Hey folks, this is Chris with Microsoft, aka Big Daddy Nines. Welcome to another exciting episode of the Performance Series. In the last episode, we were talking about processor performance, and we are now moving on to network bottlenecks. One reason that I saved networking for the last isn't because it is less important, it is just less common. Now, when I say less common for network troubles, I don't mean that having network problems is less common than, say, having disk problems necessarily. Network problems are actually quite common. However, most of the time when you have a network problem, it's not one that you experience on the box itself, or rather you could troubleshoot or even find a solution to on the box. Most of the time when you have a network problem, it's a problem like this. And I know this is kind of an interestingly naive looking drawing, but this is really the way it is. Like, you've got your data, I've got my data, we've got our awesome networks, and there's some sort of latency going on. And of course, latency, again, is similar to talking about disk latency. You know, packet latency on a disk or packet latency on a network are very similar. The difference here is you're pretty much stuck by the least strong notch in the chain, if you will. We're all going to get held up by whatever is out there. Like, I've seen 10 megabit bridges, network bridges, that would keep two very fast networks from being able to communicate with each other because somebody slapped a cheap piece of equipment to solve a problem with cabling or something like that. What ends up happening is we're all queuing up packets and able to get data from one place to another, and we start thinking, well, maybe we need to troubleshoot our server. And people will. They'll get on their server and they'll troubleshoot there. And most of the time, the problem is not on that box, so trying to troubleshoot it from that box can lead you down the wrong path. In other words, just to take for example, if I was the me in this picture that we're looking at, and you were the you in that picture, and I'm thinking maybe there's a problem with my server because I can't get data to you, and then I go in and I start pulling up performance counters and I start looking at process counters and trying to see which of my processes are generating the most data. And then I find that this one process, this poor little sucker that's running on my box, happens to be the busiest process from a network perspective on my server. We might all point at him and call him the problem because, well, we're having a network problem and he's the busiest one, right? So that's definitely got to be it. No, absolutely not. He's just the one with the biggest workload that happened to be on network doing things at the time when things were slow. So don't do that, because the problem was right out here in this not so awesome network in the center. So we need to make sure and rule out problems outside of the box as well, such as a top of rack network switch that is way overloaded. If you've got one of those 48U racks and you've got 40 or 42U racks and you've got 40 servers, 1U servers in it, and you got one little switch up at the top that is getting overwhelmed with traffic and one little uplink port to the rest of your network, that might not be enough. So you've got to kind of look around and see where the problem might actually be. And for that, you sometimes need to understand your topology somewhat. That doesn't mean that the problem isn't always on your box. It's kind of rare, but it does happen, and we need to know how to spot it. So obviously, if you were having a network difficulty live, you'd probably be looking at the resource monitor or, of course, as usual, task manager. And these are the new views of task manager. We've been looking at this through the whole series. And as you can see here, I already have my Ethernet switch, and it's sitting here throwing me little spikes and giving me ideas of what's going on as far as network utilization on this device. And so from this I can infer that we've got some spikes up to 100 kilobits per second. That's what you can see in the top right of this 100 kilobits. Well, obviously this isn't a 100 kilobit network. This is a 1 gig switch. It's scaled this graph for me so that I can actually see pretty things on it. But people will look at a graph like this and assume, oh my gosh, see, I'm spiking off the top of the graph here. Well, only if you have a 100 kilobit per second network, which you don't. So this graph you need to take in, kind of a grain of salt. Resource Monitor is quite a bit more of a useful tool than Task Manager is. Once again, this is for troubleshooting live. Troubleshooting live versus trying to pick up the pieces of what happened last night by looking at your black box counter, as we've discussed in the past, and we'll be discussing some more in the future. In one of the supplemental episodes to this series, we'll be talking about how to set up a really good black box counter, or an in-flight data recorder if you prefer. Always running data collector set that you could come back later and see what kind of network utilization you would have. So breaking out here really quick, processes with network activity. I've just got some processes listed here that are actually using some data on the network, like not surprisingly Outlook. Outlook has a tendency to use quite a bit of network activity because, well, it's getting my email and sending my email, right? One of the neat things about using Resource Monitor to troubleshoot a live problem is that when I'm doing this, I can actually kind of zoom in and see how many total bytes per second that I'm sending and receiving, or total off of this. I can sort by which process is creating the majority of that data. What's really neat too is when I checked the box for Outlook, I can come down here under network activity. You can see what I'm connected to. So you can see there's some IP addresses of the servers that Outlook is out and talking to, and which ones of them are actually having latency right now. Send byte, receive byte, total byte second, not latency, sorry, just the amount of traffic that I'm sending to each one. For instance, right now this 68.18 address seems to be the busiest one that Outlook is connected to, but it is connected to multiple endpoints out there, probably for various different services that Outlook is performing for me. I can also see these from a TCP connection standpoint. That's quite a bit busier here. You can see all the local addresses are the same because this is obviously this machine's local IP address, but then you can see the remote addresses and what port they're on. And you can see they're all connected on 443, and that's because this is Outlook and it's going through Office 365, so that's all going to be 443 traffic. And then finally, listening ports. What is Outlook actually listening from a local perspective on this box? Some of the others grab something else in here. So maybe, Team Viewer. What does the Team Viewer server look like? This can be kind of useful if I need to ever look at that. So you can see that it's connected to that PID. It's connected to this address, that remote port, and there are no listening ports on it, so that's interesting to know. And you can see where this can get really handy. So troubleshooting live problems and seeing live network data would be Task Manager, Resource Monitor. If you prefer sysinternals utilities, here's one's called sysinternals TCPView. And so you can see there was a little green thing that lit up there for a second. That meant a new process. We see some red stuff in here. Those are ports that are closing right now. And these ports are always going to be in one of a few different categories, either time wait or close wait, established, listening. And what those are telling me about all the ports that my box has, are we connected on them? Are we currently listening to somebody to connect to us on them? Or are we in a closed wait or time wait like these guys up here? Time wait will stay for a certain number of seconds because we had a reset instead of a fin. And if you're not familiar with what that means, we'll have a session on Netmon coming up, and that'll give you a little bit more information about what the difference is on a time wait and a close wait. But they will sit here for a period of time, making sure there are no more data packets that need to come through before these shut down. So this can be a little bit better, in my humble opinion, than what you've probably used a time or two before, such as netstat ANO. When you do a netstat ANO, you can see that I get kind of a similar view here, but with a whole lot less information of each one of those. So this is kind of, once again, sysinternals making a known tool like netstat work a whole heck of a lot better than it did in the past. So these are all great for telling what your box is doing, telling what is going on out on your network connection when you have live data. But obviously this whole class, this whole series is all about how to use perfmon to troubleshoot these things over a period of time, run a capture, get data. So a couple of little things about perfmon and understanding what limitations you have using perfmon to troubleshoot network issues are understanding what you're looking at. So if we were to create a data collector set, and we'll call this network, and we'll create it manually, and we'll do perf counters just like we have in the past. We're going to add in a few different counters, and these are going to be under the network object. So we'll come down here to network adapter, and we're going to go ahead and grab my, holy heck, which one of these do I need to get? So really quickly going through here, it's probably that gigabit network connection. There are a few counters that are important here. So one is bytes received per second, and then we have bytes sent per second. We do not care about bytes total per second, because each send and receive has its own channel. So you have if we're on a gig network, which you can see that we are, and we have a receive channel and we have a send channel, then we have 1 gig of send and 1 gig of receive, so we need to measure those differently. We need to compare those against the current bandwidth. The current bandwidth is simply, are we connected at a gig? This is very important to make sure you got it in there because it's part of an equation we'll be using here in a little bit. But it's also important to have that as part of your measurement because we need to make sure that that is at the expected connection speed. Don't be fooled by thinking that just because you've got a gig switch plugged into a gig NIC on your server slash workstation slash laptop, whatever it happens to be, that you're actually getting a gig, because you will not always get that. And that can be caused by additional problems outside of the box, and we'll talk about those as well. Okay, more counters that we need is the output queue length. This will tell me how many packets are waiting to get onto the wire. These are packets that have already been assembled, TCP/IP packets that have been assembled by the operating system, and they've been sent on their way, but they are still not past the network card. They're still sitting on the box, and they haven't actually gotten out on the network. Special note about that counter, it is broken in 2008 R2 as far as I know. I've never seen it over 0, so I have to assume it's broken. Same thing with Windows 7, Windows 8, Server 2012, everything like that and higher works out just fine. Best that I can tell. Those didn't seem to work in 2012 R2 or 2008 R2. So slight problem there, but most of the time with more modern operating systems they'll work just fine. And you might be justly thinking at this point, so where's the latency counter, right? I don't see any counters here, Chris, that would indicate like, packet delay sent per second or average disk sent per second type of counter here on the network side, right? Because we've got the average disk per second read and average disk per second write. There are no counters that measure latency in perfmon. Now, we saw some latency stuff when we were looking at the tools we were looking at a minute ago, but there are no latency counters that are available in perfmon. There's just not a way to do that. So a next logical question you might have is, okay, well, what about process counters? Yes, we do have those. So if we have the ability to measure how much data we are receiving or sending on the network, we should be able to break that out per process. And we do have them here. However, I will say, once again, that a lot of times going in and seeing that you have a lot of latency on a server and then coming in here and doing process analysis, that's not a good idea. You need to rule out the rest of the network first. We need to make sure that our problem is not someplace in this area right here, right? We don't want to be troubleshooting something here or here when the problem is here. Right? And likewise, we don't want to go send this back over to the other department and start accusing them or their network of a problem when the issue is here. Right? So that's a big piece of understanding how this works. But just the same, I'll show you how to do a process analysis on this as well. So as such, we must have all instances of the process, and we need the IO other operations per second counter because IO other bytes. Whoa. Other bytes per second will measure the amount of network activity, for the most part, that's coming from your processes. And that's really about all that we have from a perspective of just kind of basic network troubleshooting on these guys. And so let's kick that down. Heck, let's do it for 3 seconds, since we're not actually going to be doing anything lengthy here. And we can kick that off. So I can show you kind of more or less what it's going to look like. What do we want to use? Maybe Task Manager here. That's probably a good one to use just to kind of see some network activity and we're going to use a tool called iometer. So what I've done with iometer, which we used once again for the disk activity, you should remember this tool. I have attached this iometer to an iometer on another computer on this network. This is a 1 gig network, and so we're going to go ahead and kick off 6 worker processes, and we're going to go see what kind of network activity we get. So run in here into Task Manager, and we'll see that that's going up. We should see the graph rescale itself. So it was at 100 kilobits per second, and that should jump up. Also for on Resource Monitor, we should see the TCP connections and the network bandwidth start to jet up as well. Here you can see we've now scaled to 10 kilobits per second, and we'll see that go up a little bit higher, and we'll see some activity go as the report finishes off. We should also see on TCPView some, the test may have already completed. Hang on just a second. Did it finish? Yeah, I must have this set to test setup to only run for 20 seconds. So obviously we need that to go maybe a little longer. Let's do that for 2 minutes now, so that we can actually see some of these tools kicking up and doing their thing. So we should see some tests going from Dynamo here over to some other servers on the network, and get it kicking up a little bit. Now let's see what we're looking at from a perspective of the network activity. So yeah, we're now showing the scale at 1 gigabit per second, and you'll see that the send is in the little dotted line down here, and the receive is in the hard line kind of in this graph as well. So we're getting some good data generated. It's not enough to fill the pipe, but it's enough for us to come back and kind of show what it would look like if we were troubleshooting this from a process analysis. This is only what's going to happen is when you actually see your network hit its threshold and want to know what it is on your box that actually generated all that data. Not when you saw some sort of latency. When you just saw latency, that's kind of a different piece to how all of this works. So the latency itself is going to show up a little bit different. That's that's a user experience. That's something you're measuring, probably with ping, right? Let me kick that test off again for just a moment, and let's. Okay, so it's still running. We've kind of run it down where it's not really doing much. So let's let that one, let's just go ahead and stop this guy here, and then let's kick him off again and see if we can get some data kicking through. Okay, I think we may have just scaled. All right, so go ahead and get some measurement of latency right there and see how many. Yeah, good. We're computing statistics. So pathping is an interesting tool because it does measure latency. So if I were path pinging, let's say, to another device someplace else out on some other network, we could path ping out to 4.2.2.2 possibly, and see what kind of latency we get. Path ping is a little different than ping because what it'll do is it'll actually run you up numbers like ping does, but then it's going to follow all of those hops along the way and tell you which ones had different latency. As you can see, Cox is the next up level provider from this right here. So this is my local router on this. Dadgummit, why do I keep doing that? This is my local router right here, the 10.0.0.1, and then 10.5.64.1 is something on Cox's end. Cox's end is right here as well. You can see I got some MTC3, OK, Cox. So those are all the hops between me and level 3, and I can compute all the statistics for each of these and see which ones had more latency than the others. You can see this report over here has now completed. We can see that we didn't really have any latency from me to my router, but we did throw a bunch of packets at them and saw that we didn't lose any packets. We had 0 of 100 loss, so 0% loss, and so everything's working from that end. So those are good latency tests. Those are good ways to kind of test what's going on. This one will take a little over 3 minutes to compute because it does so many for every hop that's in there. So you'll see this 200 seconds if you have 8 hops, for instance. So anyway, we'll let that run for a second. We'll take a look at what path ping is going to look like. Looks like iometer is pretty well done done running its thing. So we've gotten ourselves some captures now in perfmon, and if I go ahead and stop that, I'll show you how to interpret these counters. And again, when you would use this would be you have determined that the problem is on your box. Maybe it is that scenario where we've got the 42U rack with 1U servers sitting in them, and one server somewhere in that rack is just flipping out on the network, right? And we need to know, kind of where that's coming from. So what do? Well, we go to that server, we run these kind of counters, and we go see what we get. All right, so we looked at the 4 counters here. Your key indicators, and just as a refresh from every other one of our commodities, for lack of a better word. We've had hard drives, we've had processors, we've had memory. Each one of those I've given you key indicators. That's when I first pull the performance counters off of a machine that I want to troubleshoot. I'm just going to load up key indicators for the sole purpose of finding out what was slow. They said it was slow, they said it locked up, they said something happened, right? So I'm going to be looking at my averages per second read and write for disks. I'm going to be looking at percent of processor utilization for processor. I'd had a handful of key counters that I gave you for memory. These are your key counters for network. Did we indeed flood the pipe? And that's average disk per second, or average bytes received per second, bytes sent per second, measured against the current bandwidth. Bytes received is obviously in bytes. However, current bandwidth is bits. Have you ever heard of a NIC saying, megabits per second? Right, that's because that's how those are generally measured. You have 100 megabit per second or a gigabit per second. They're all in bits per second. So there's a calculation I have to show you to make these line up to those. And if we throw these 3 counters in there on our gig network connection, kind of show you what these look like. Let's scale that graph out where we can kind of see it. And you'll also see by me scaling out that we're going to see an interesting pattern here. So if we were to turn on the highlighter and click right there, you'll see that that is my current bandwidth, and the data was much higher than that, right? So why would the data be higher than the actual bandwidth? Well, it's because that's just the way it is, and I mean that not facetiously, I mean quite literally. It's in bits and those are in bytes, so work accordingly. We go ahead and bump this up just a hair more so we can get this guy up on. There we go. That was perfect. Okay, so now we can see the send bytes right here, or receive bytes rather here, and we can see the sent bytes there, and we can see them on the graph. But the bandwidth itself is not going to be a whole lot of use to us because it's in its present form. It is useful to me right now because just from right here I can see, using the data below, all of these things are at 1,000,000, right? So when we look at these, and I just realized that my zoom feature that I've been going through this whole thing may or may not be getting picked up, and so I'll have to go back and possibly edit that. But right here you can see that we're at 1 billion. So if we're at 1 billion, what does that mean? That means that we are at 1 gigabit. We're doing 1 gig. And that's important because if I was expecting this to be at 100 megabits per second, or if it's at 100 megabits or 100 million, then what I would know is that, hey, I've got a gig network, but for some reason the daggum thing's connected at 100 megabits per second. That's a problem in and of itself, right? So we would want to, at that point, be investigating, hey, did somebody downclock this? Has someone hard-coded the driver to only connect at 100 megs? Is it possible that whatever my switch is that I'm connected to has an iOS, if it's a Cisco switch, that's not getting along with the firmware? Are the drivers on my own network card out of date? Stuff like that is what you're going to be looking around at. It can even be a cable. A bad cable can cause this to fluctuate and the handshake just falls off, and then what you should be connecting to at a gig fails back to 100 megabits or even 10 megabits, which would be just terrible. So there's a formula here, and it's not that hard once you've done it a couple of times. So let me pull the formula up and get that here. It's bytes sent per second times 8 divided by current bandwidth times 100 will give you the exact percentage of where we were at. So what we need to look at here is we need to go to our bytes sent per second or our bytes received per second. Let's look at that. Pull the calculator up. So we can see that at a maximum value is right down here. So let's pop that in there, 115, and then 535, and then 559. Now looking at our handy little double clicking things that I don't need to double click, sorry. So you see, because it's a bits to bytes conversion, we're going to take that, we're going to multiply it by 8, and then we're going to divide it by that current bandwidth number, which was 1,000,000,000,000,000. Then we multiply that by 100, and we can see that we got to 92% of the network utilization in this case. And that's what I was trying to explain earlier, where there's a send and there's a receive. So we can see that in this case, we did indeed get up pretty darn high. In fact, if we were to set a percentage counter on this, anything as far as network related sending and receiving that is above 30% for a sustained period of time is a problem, and over 60% is where you need to be alerting. We were at 92% at the maximum. Now obviously if I took the average, that's going to be a little bit less impactful, but the average was probably a little bit less than half that. It's still at 40 something, so we'd be in warning right there. And the reason for that is because of all the overhead of TCP/IP. Now these are two servers sitting on one's a server, one's a client, sitting on 1 gig switch, and therefore they were able to get kind of close to the theoretical maximum value of the send at 1 gig. All right, so moving on, if you were looking at the receive, it's the same thing. It's just the exact same other counter. Instead, we would be, of bytes received per second, we use bytes sent, whichever one you're measuring, it's the same formula. So just amount of traffic times 8 divided by the upper limit, theoretically, of that channel they're on, and then multiply it by 100 to get a percent value. And again, 92%. So in this case, we did in fact find a process that we'd created that was really, really high utilization. And if you are in fact searching in your rack for one server that is higher than everybody else, make sure before you start going into process analysis, which we're about to do, if we were going into process analysis and taking a look at this, what would we expect to see? We'd expect to see a process on the box that is in fact pulling that kind of data across. Don't go looking at every server and looking at process analysis on them. Find out which box it is that's causing the issue first. So switching back over here and then adding in our process counters, and we'll cheat just a little bit because we know that it was Dynamo, just so that we can get that out there. So we've got IO bytes per second, which we've thrown on here. So he is scaled a little differently than those guys. You can see that his default scale was 1, and they're all at a 0.001. So let me try to change his scale, and let's see where that gets us, and kaboom. So fairly obvious pattern there, right? So red being the bytes received per second, and the black highlighted one right now is IO data bytes per second. So we see a pattern here. We can see that there was one server in this theoretical rack of servers that was just freaking out and overwhelming the switch. So you might say, okay, well that's great, Chris, what do I do now? Well, you need to go find out if that's normal for that process. Is Dynamo supposed to be doing that? And if so, do we need to get it into a server with a 10 gig switch? And maybe team those NICs or something. Give them more data. If this is an application that truly needs that much data all the time or in bursts, and there's not any way around that because it's just what it does, maybe a backup server that pulls backups from just dozens and dozens of other servers around your network, then yeah, you might want to expect that he's going to need a little more bandwidth than whatever you've got him here at. And that's going to be measured by whether or not you have created and seen an actual problem out on the network. All right, so this again is what you would do if you were doing process analysis on the local system where the problem occurred. And from here, we should probably also add in the one other counter, which is the output queue length, And we'll put him in here, and we'll go ahead and highlight him just to talk about him. You'll see that he's 0. Now, does that mean that there wasn't a problem? No. What it meant was that even though we threw lots and lots of data at this thing, the whole time we were running that test, it never really freaked out. That just means that the switch was able to keep up, the NIC was able to keep up, all of the network infrastructure pieces were able to keep up, and it never had to queue any packets. Right? So there isn't a terribly good measurement for this, but I would say that if you're seeing 2 or 3 packets that are constantly sitting on the wire unable to get off, you've overwhelmed your switch, got a bad cable, you've got bad drivers on your NIC, or you've overwhelmed your local network card. So again, our biggest key indicators here are going to be the average, your bytes received per second, and your bytes sent per second after putting it through our magical little formula here. Comes to a percentage that is consistently over 30% we're warning, over 60% we're alerting, and output queue length is at 2 packets sustained, we need to warn, and if it's over 2 and it's constantly like that, then we need to definitely I'll be alerting for that because we're having trouble getting packets on the wire. Okay, so pulling our little path ping back up here, and let's take a look at what kind of report. So in my case, I obviously did this across the internet, but if you were to take this same kind of test from one subnet in your own network to another, what it'll do, assuming that you don't have any of your devices blocking ping, in which case you would see 100 here fails out of 100, and then it would say 100% fail, and then obviously that's not true, because if you have anything below that, then what that means is that you simply had one device that was not responding to ping, but you were able to get through it. But here's the cool thing about that test, right? I can tell that was 1 millisecond, this hop was 9, this one was 10, this one was 11 milliseconds, this one was 36 milliseconds, now we're back down to 17 milliseconds for the next hop, 19 milliseconds for the next one, and 15 milliseconds for the next. So we can see at each hop what kind of latency I'm getting for all of these different devices, wherever they happen to be in my network or out on the interwebs or wherever they are. So this is a good way to kind of identify where the hop might be that is causing you to run into this condition where you got something you're trying to send to me and it's just taking way too long to get there. So path ping can be kind of useful. Again, that is not a perfmon tool, obviously, so you're not going to be able to troubleshoot that through perfmon. You're going to need to troubleshoot that live as the problem is occurring, as with many other network problems that you'll see. And that's one of a number of tools that are in your tool bag for identifying problems out on the wire. I should probably also mention another common gotcha that you'll find, and that's when you're looking at the current bandwidth counter. So let me show you, let me find a system here real quick that we can pull up and look at that's got kind of a bizarre looking counter. All right, so here's one. So this one always scares people, and it's not actually scary. So what we're looking at here is a 1.0000E plus 010, which always terrifies folks. This is actually a lot easier than I think it is. All it means is add 10 to the right of me. In other words, I can only display, up to 10 digits. So if you were to move that decimal place of 1 dot to the right 10 times, what would you have? You'd have 10 billion, right? Because that's how many zeros that you have behind 10 billion. 10 billion is 10 gigabits per second in this context for the current bandwidth. So if you got a VM, you'll see this very commonly. You'll see this number. So the same calculation that I gave you before works, just obviously don't try to plug 1.0000E plus 010 into your calculator. Put a 1 with 10 zeros behind it. meaning 10 billion, and then that will be your counter. Why do you see this? 10 gig E is a real thing. On virtual machines, 10 gig Ethernet is actually what the NIC thinks that it's connected to the host on, and so that can throw your percentage counters off a little bit. So you got to know what your host is actually connecting with, and maybe it is 10 gig, and make sure that if it's a 10 gig NIC, it's not partitioned into a whole bunch of little 2 gig NICs. That's something else you'll see, and I don't have a oh, maybe I do. I have one system that I have an actual team running on. Let me pause the video and go see if I can get some counters on that team. One sec. Okay, here we go. This server has a network team on it, so this should get us exactly what we need. So let's go up to the network object here, and let's go find the Microsoft multiplexer default. I can't remember if it's the driver or the mini port. We'll just go ahead and dump them back in there. Okay, so what we're looking at here on current bandwidth, dump those. There we go. There we go. So this is what I was looking to see. If you can see that it's actually showing at 4 billion, which is a little bit weird. We don't have 4 gigabit Ethernet adapters. I know there's 4 gigabit when you get into fiber channel, but how would we get 4 gigs? Well, the reason we have 4 gigs per second on this one is because this guy is a 4 NIC team. So he's got 4 gigabits of throughput, and perfmon is intelligent enough to actually see that as its current bandwidth counter. So a couple of weird things that you might see from time to time, you know, the 10 gig 1 plus E type of scenario, odd values like this on your current bandwidth. So just remember to use those. That's an important piece there, even though they may be a little bit weird. It's kind of think of it as similar to having 400% processor utilization by some processes. It's just multiple cores, in this case multiple NICs. Another good thing to know is what can your network do when things are not having a problem, or what can you expect out of them when we have things running like what we just did. So you can see that IOmeter has this nice little report that it finishes off with that'll tell you total IOs per second and megabits per second, etc. This is a really handy test to run from one place to another, and it's not what most people do with IOmeter. IOmeter is normally what people are using to benchmark their disk performance, but you can do this with network as well. So let me show you how to set that test up, because this is certainly a little bit better than a file copy test, which is good. I mean, you can use fsutil and dump a 200 meg file and dump it across your network, make sure it gets there in a couple of seconds, and things are a pretty good benchmark that they're working okay. But being able to actually measure to this level can certainly be handy. So let me pull, that's the wrong server. Let me pull up, I keep pulling up the wrong server. Let's go to the server here, Mr. Hyper-V. All right, so here's the IOmeter piece that I did. So the command's actually pretty simple. I'm going to go ahead and stop this. Now, it should be right, yep, there we go. Okay, so point being here, you see that we are doing dynamo and then -I, and then some IP address, and then -M, and then an IP address. So first thing you do is you fire up IOmeter, and we'll go ahead and close it. Just actually, let me pin that real quick so I can reopen it really fast. Okay, so I've closed IOmeter. Now I'm opening IOmeter back up again and getting the UAC prompt, and up should come IOmeter, and there it is. Okay, so first thing you do is come in here and dump out all your disk workers. Just click the disconnect thing right there, and lovely, I just disconnected my computer, so let me reconnect that and then dump the workers out again, being a little more cautious not to dump the computer itself. Okay, so all I have now is the managers and then my own machine, and then the next thing I'm going to do is I'm going to fire off Dynamo right here, because what I'm telling it is, hey, this is local machine .22, and that's remote machine, or that's remote machine. So we're on this Hyper-V server, right? And that is not this box, okay? So this is my local system, this is the remote system. And so I put the remote system in first under -I, and then I do the local system -8 right here. What he's going to do is he's going to connect to IO meter on my box, and you'll see that he has now appeared there. And he has by default thrown in some disk workers. I don't care about the disk workers on a test like that, so I'll delete them, and you can see that he responded down in the Dynamo thing here that we had. So once again, that command was not IO meter and then some -I and IP addresses. That was Dynamo. So you need to get that from the same place that we talked about in the disk section, that IO meter is available out on the web for free. And you pull that down. So now what we're going to do is we're going to do a network thread. So I'm just going to put the one worker in here and show you what it looks like when I'm looking at the network target. I've got this 10.0.0.8, that's the remote system, and you'll notice that after I tick the box for that remote system, it shows up as a shadow worker here. And I could do that again just to kind of show you. So worker number 2, I'll connect him, and another shadow worker has appeared. And so then we need to create some access specifications. So disk counters won't do you a whole heck of a lot of good. So what we need is to actually go create one that is good for network testing. And let me grab that real quick. And here it is at itechstorm.com. I found this, and I'll put a link in the description below. It's /network bandwidth testing IO meter, where he's wrote this really nice blog. This guy Yodabyte, I guess, wrote this. This is where I always like keeping my bookmarks, because down here towards the bottom, and there's a step-by-step walkthrough for getting this started. This is the access specifications for the test. So that right there is what we're going for, right? So how do we do that? Well, we come in here and we say new, and we're going to do a new test specification based off of what I found on that site. And so we're going to call this net test or something similar to that. And I'm going to go ahead and have that as a default assignment to network workers. And then there's just a couple of changes we need to make. And the first one is transfer request size needs to be 16K. And notice that I put that under the kilobytes section. And then the next thing is the percent of access specification should be 100%, which it is. And then the random/sequential distribution should be 100% sequential. And it's random right now, so we move that over. And then transfer delay should be at 0 milliseconds, which it is by default. And then the burst delay length should be 1, which it is. And then assign IOs on sector boundaries, so we'll need to change that radio button right there. And then reply size should be no reply, which it is. So as long as you haven't got anything changing your defaults here, this test should be 3 changes and you're good to go. And after doing that, it has put that in net test right here, so I just add it into my tests. Go to the test setup, and what I like to do is go ahead and take the record results and turn it to none. That way it's not always asking me for some field or a CSV file. But if you do need to save this to a CSV file, you can put that on here for the targets and workers that we're going to be running. And we can go ahead and just make sure this doesn't run for too long and maybe say run it for 30 seconds. Go over to the results display, click the green flag, and let's see. Oh, worker 1 didn't have any. So we need to give him one too. So worker 2 and worker 1 both have those. Back to results display, click go, and you can see that IO meter remotely began to run its test, and it is running right here on this box. And so now we'll let that run for its 20 seconds. Pause the video, come back, and look at the report really quickly. Okay, it has completed its run, so you can see that we can see how many input-out ports per second, megabits per second, average I/O response time. You can even drop some of these down and see other pieces of the report that just don't show up by default, like maybe average latency, read response, or write response. You can see this is in milliseconds, and we can see where this got up to. So a lot of good detail here to give you some idea of what your box is getting to. The next logical step for troubleshooting here is obviously going to be jumping out and using something like netmon, which is way beyond the scope of this, and we're already over the time that I had planned on for this episode. We're coming up on 45 minutes. So this is just basically how to get started trying to determine whether or not your box was the problem, and if it was the problem, how to figure out which process on the box was causing the problem. And that's probably as deep as we want to get until we get into some of the supplementary parts of this series, talking about things like netmon. So we'll probably go ahead and call it there. So anyway, folks, this has been Chris with Microsoft, as always. I appreciate you watching. If you did find anything about this useful or interesting, take a second and give it a quick like. That'll help other people find similar relevant searches to this material. Also, feel free to subscribe to my channel. That'll give you notifications whenever I put up a new episode. Also, my blog is at 9z.com. Seriously easy to remember. It's just the last number and the last letter .com. That's also got links to my Facebook, my LinkedIn, my Twitter, my TechNet blog, etc. So again, as always, thanks a ton for listening, and I'll see you guys in the next episode.